super jam-packed. I might end up splitting it into two parts up front, depending on length, just depending on how it goes. But so, because there's a lot to cover within this, I think the best place and the first place to start before I dive into any of this is like, how exactly did I start on this like crazy track and even uncover any of this, right? Like, what's like how do you get from like A to like Z? And essentially, I started off with the question of trying to understand what the base language of AI is, like what the base language of an LLM model is specifically. And because an LLM model doesn't use binary, it doesn't use English, it doesn't use like like Chinese. There's no like structure that I can understand that is its base language, and it's not graphs. And so I want to understand what. That was my first question, right? Like how does it work? Like what's it doing before it translates to tokens, or like for like, so it's X to tokens to English to or like, and so what's that, like what is X? And within that, I start finding out more and more that X is related to shape and shape of the data sets. And I can start proving this more, right? And there's more and more studies that come out that can prove this, that this shape exists. And there's a lot of studies that come out and they start coming out on all different aspects and areas of the shape. We can measure the gravity of the shape, the torque of the shape, the distance of the shape, etc. The problem is that the shape is not stable. It falls like every single time that you measure the shape, it's like taking a snapshot of this shape. And I start pondering that problem like over and over again. Like why does this keep happening? Because the shape is there. Like it's 100% there at this point, right? I'm convinced for a long time that it's there, but I can prove its existence, but I can't prove the shape of the shape. And then so I start struggling with that problem for so long. And then it just eventually hits me. I think I start with diffusion, right? And like I start thinking about it through the lens of diffusion, which is important, which we'll get into when we get into the Navier-Stokes network. But I'm like, diffusion is it's a liquid process. It's governed by thermodynamics. It's governed by temperature. It's governed by fluid dynamics. Like there's a lot of correlation between fluid dynamics and diffusion. And then I start thinking about that and I'm like, well, like how exactly does like HDC work, and how exactly are these models doing other things? What's the LLM, like what's the like, so I know that the model is turning and dialing a shape. What's the physics behind that? It has to be governed by physics. And then I start thinking more and more, and the more I kind of deduce and isolate, I start coming to this weird conclusion that fluid dynamics is involved in this. And then I end up being able to prove it out. And then so that's exactly what I have at this point. Beyond a reasonable, like any doubt whatsoever, I have mathematical proof, the experimental proof, etc., that AI and information are very explicitly governed by fluid dynamics. And so the premise is very simple and straightforward. Data is governed by fluid dynamics. And I established this both in my previous video on this, and then we're going to look at my GEMINI experiments very specifically. But data behaves like a fluid, meaning it exhibits flow-like behavior, movement across networks, memory, and computation. It has viscosity. It has resistance to compression and transformation. And this viscosity varies depending on data sets, and structure is the lever of the viscosity. A more structured data set is more like a solid, less viscous, and that it's more resistant to change. The other variable that you have within this is turbulence, so chaotic fluctuations in high-dimensional data representations, as represented by such papers as like torque torque turbulence, and everything that is related to essentially like gravity, and the elements that we can relate to distance within this. And then you also have diffusion, which is the spread of information over time. But I will show within this, and within the overall variable of the kind of like Newtonian liquid structure of data itself, or the non-Newtonian structure of data itself, that within that time, time has a slightly measurable impact, and is a variable within it, but it's not significant, at least according to my measurements. It's a non-Newtonian liquid that is not directly impacted by time steps. So since AI models process and transform data, the behavior of data directly carries over to AI itself. The fundamental nature of AI, optimization is a flow. AI, particularly neural networks and machine learning models, operate through a form of gradient-based flow dynamics. This is like all known, like every essentially neural network utilizes gradient descent, right? And then so it's like baked into AI at this point. And then so reason why, gradient descent equals fluid flow. The weight updates in AI models follow a path of least resistance, similar to how fluids follow pressure gradients. Mathematical equivalence, the backpropagation process in AI models can be described by partial differential equations, or PDEs, which are also the foundation of fluid dynamics. It's the foundation of a Navier-Stokes equations, and we can literally use just these Navier-Stokes equations to build a neural network, which I'll show you in this video here as well. So information propagation equals wave and diffusion dynamics. AI systems spread and refine information in a manner that mirrors wave propagation and diffusion in fluid systems. Natural ODEs, or ordinary differential equations, treat feature evolution as a continuous process equivalent to fluid evolution over time. When I first started tackling this problem, I tackled it very specifically from the geometry standpoint. And then I realized that there's like, of course, the wave function and wave functions and resonance start playing impact within this, right? I can't discount those variables within the equation. I can use geometry to measure shape, but then I noticed that there's impact on this shape based off of a wave, and essentially what ends up being diffusion dynamics. And when you put all of that together, the only way that you get those dynamics is within a fluid state. And then so that's where I start drawing that conclusion. So conclusion, AI learns by following fluids-based optimization principles, which are deeply aligned with fluid dynamics. AI model behavior is identical to fluid systems. Now, let's examine 3 core properties of AI models that mirror fluid dynamics. A, turbulence in neural networks or fluid chaos. Observation. Deep learning models exhibit chaotic behavior in observation landscapes, similar to how fluids develop turbulence. Supporting evidence. The Kolmogorov cascade, which describes energy dissipation in turbulent fluids, is statistically similar to gradient-based learning in AI. AI models, particularly deep networks, show scale invariant structures, a hallmark of turbulence in fluids. Conclusion. AI models exhibit turbulence-like properties in their weight dynamics and loss landscapes, confirming a deep connection to fluid dynamics. B. Entropy, diffusion, and viscosity in AI learning. Observation. AI models spread and compress information in ways identical to fluid diffusion. Supporting evidence. Entropy regularization in AI follows the same statistical rules as entropy dissipation in fluid systems. Overfitting prevents techniques, for example, dropout, batch normalization, they mimic viscosity effects in fluid flow, introducing controlled resistance to smooth out learning. And I can prove this to you up and down, and I will show it to you up and down. Conclusion. The flow of information in AI obeys principles of viscosity and diffusion, further reinforcing the AI-fluid link. C. AI computation as a Navier-Stokes system. Observation. Neural networks, particularly modern architectures like transformers, can literally be written as Navier-Stokes type equations, which I'll show you, supporting evidence. The state space representation of AI models can be modeled using fluid dynamic equations. I'm going to show it to you up and down. Researchers have already designed machine learning architectures based on hydrodynamic principles, confirming the feasibility of AI as a fluid system. Conclusion: AI processing follows structured flow equations, much like physical fluid systems. The final step: AI is information, and information is a fluid. Since AI is built upon data, data is governed by fluid dynamics. AI models behave like fluid systems, meaning diffusion, turbulence, and entropy flow. It logically follows that AI and all forms of process information is governed by fluid dynamics, a paradigm shift. This means computation itself is not just discrete logic, but a fluid system, suggesting AI architectures should be designed using fluid principles. Future AI models may integrate hydrodynamic constraints for better efficiency. I'll show you this model starts performing better, which there's some simple tweaks, than traditional neural networks. Information theory may need to be reformulated as a branch of fluid dynamics. As a summary of this video, everything that I'm going to go over here for you is one, that the data behaves like a fluid, meaning a viscosity, turbulence, and diffusion. I'll show you via this GEMINI model. AI optimization is a flow process which utilizes gradient descent, which mimics fluid flow very specifically and is a process of fluid flow. 3. AI models exhibit turbulence, entropy diffusion, and wave dynamics. 4. AI structures can be rewritten as Navier-Stokes equations. And 5. Since AI processes information and information follows fluid dynamics, AI itself is a fluid system. Conclusion: in this video, we will redefine AI through the lens of fluid dynamics, proving that AI is governed by the same physical laws as flowing liquids and gases. So let's get into this, right? First thing is to prove the data part of the equation. And so I do this via GEMINI. And then this is the notebook interpretation and introduction of GEMINI for you. I have the full mathematical equation, so if you're interested more in the mathematical breakdown and structure of GEMINI, I have it available in my GitHub repository. And so GEMINI stands for Geometric Embedding Manifold Interpretation of Non-Newtonian Information. Introduction. The GEMINI framework provides a novel approach to understanding and analyzing data by drawing an analogy between data and non-Newtonian fluids. It leverages geometric embeddings and manifold interpretations to characterize the behavior of data under various transformations, particularly dimensionality reduction. Definitions. Data as a fluid. Data points are viewed as particles suspended in a fluid medium. The relationships and structures within the data define the fluid's properties. Geometric embedding. Dimensionality reduction techniques are used to embed high-dimensional data into a lower-dimensional space, akin to applying shear stress to the data fluid. I go through and apply multiple tests. Manifold interpretation. The embedded data is interpreted as residing on a manifold, a geometric surface. The properties of this manifold, for example, curvature deformation, reflect the data's structure and behavior, non-Newtonian behavior. The data fluid is considered non-Newtonian, meaning its viscosity changes with shear rate, shear history, or other factors. Key metrics: shear rate, the degree of compression or dimensionality reduction, in, for example, perplexity in the T-SNE equation or the T sign, shear stress, the force applied during compression, like for example, information loss, viscosity, resistance to deformation quantified by the viscosity score, deformation, change in data structure due to compression measured by compute deformation, and recovery, the extent to which data recovers its original structure after compression measured in viscoelasticity experiment. All of the experiments that you would do around non-Newtonian structures and everything that you would expect to happen with non-Newtonian structures happens with data. It's just no one's ever done it. So here's the mathematical formulation here. Again, the full mathematical formulation is available and more readable on my GitHub. So my experimental evidence. The evidence is that the viscosity measurement, different data sets exhibit varying viscosity scores, confirming the non-Newtonian nature of data. 2. Shear rate dependence. Viscosity changes non-linearly with perplexity, the shear rate, showing that shear thinning and shear thickening behavior, meaning that you can add like a solvent or paint thinner to or paint thickener to data sets and it works. Hysteresis. High viscosity data exhibits hysteresis with viscosity depending on shear history. 4. Viscoelasticity. High viscosity data shows partial elastic recovery after deformation. Applications. Data characterization. GEMINI provides a new way to characterize and classify data sets based on their non-Newtonian properties. Dimensionality reduction. Informs the choice of dimensionality reduction techniques and parameters based on data viscosity. Machine learning can be used to design more and efficient machines and data visualizations. Here's the proposed equation. Again, it looks much better on my GitHub as far as the equation goes. So going into, and then all of this is MIT licensed up front. And then going into the notebook itself and into essentially the code here of the experiments, right? So the first experiment that I do is essentially I design upfront 3 data sets within this, and the 3 data sets I assume will be a high viscosity, which is a structured data set, medium viscosity, which is low, like an embeddings data set, and low viscosity, which is just pure noise, right? And then you can go through, and I structure the data sets the same way every single time. And then I go through, in this first experiment, we're just essentially measuring and trying to compute the the liquid metrics of these different data sets, right? Is there a difference, a liquid difference that can be detected between these 3 data sets? And then so I run essentially like the same test that you would run on liquid. So I compute entropy using kernel density estimation, compute curvature using PCA explained variance, compute deformation, so the distance changes after compression. And then I run the experiment, I apply the experiment, and then here's the results. And then we show that our structured data set it's an outlier. Like there's a definitively we get more non-Newtonian the more structured the data set gets, and then the less structured and the more close to noise that you get, the more Newtonian that it gets, the closer that to a Newtonian liquid that it gets. And that's kind of like this curve that we established right here from jump with the first experiment, right? And then so from there, it's like, okay, I've established that this curve exists, and then let's just prove it out in multiple ways, right? And then so next experiment is let's test individual portions of this non-Newtonian liquid. So my assumption up front is, okay, we've established that it's a liquid. At this point, this first experiment, I don't know if it's non-Newtonian. Let's test that. So I set up experiments, so same data set, same experiments for the synthetic data set, compute entropy kernel using KDP, compute curvature using PCA, compute deformation using all pairwise distances, run the experiment using PCA components, so I'm using dimensionality reduction. In this instance, generating new seeds for every single trial. I alternate viscosity formulas in this instance, so I'm making sure that I'm testing viscosity, does viscosity actually exist within this, right? And go through, and then here we go. And then across different, multiple, a multitude of different scenarios and different trials, and essentially for 30 trials in this instance, we get the data confirms, right? There's undeniable. We've got our viscosity metrics from the different data sets. The differing data sets do have differing viscosities, and they do measure out to computable differences, especially within our structured data set. And then we go through, and then I want to do more tests within this. So essentially, next thing is like let's test this further, right? Let's test like the non-Newtonian structure of this, and then do more tests. And then so I do like essentially like every single like non-Newtonian test, liquid test that you can do, as I mentioned essentially at the top of the video. I don't want to get too into weeds here, but so this is the viscosity versus PCA components. Again, clear differentiation between high viscosity and low viscosity data sets, and all across the board, across every single metric, what you can see is that we have this detectable viscosity metrics, and these are exactly what I would expect to see if I were measuring a non-Newtonian liquid flat out. It just all correlates, right? And then so I don't do it. I go through and then like more tests, right? So let's test different aspects of this. So let's test the viscosity versus mixture proportion. Does that make a difference? Like, and I would expect that a graph would do this with a non-Newtonian liquid. And then so here we go. Exactly what we would expect, again, from the behavior of non-Newtonian liquids when I test data sets as non-Newtonian liquids. And then I go through and then like let's do a different test, and this time let's do viscosity versus TSNE perplexity. And then in this instance, it's kind of a weird test, right? But again, it's in this instance, it's showing that like there's no like time isn't a huge impact on this, which is again very corollary to and very expected within this instance because of like how some non-Newtonian liquids work, right? Like a lot of liquids are very time dependent, but this is showing that like there's like very minimal time relationship. It's not zero, but there's a very minimal time relationship between this the liquid that we will call data and time itself. Very small correlation that exists, which is like unexpected overall with liquids, but not like there are numerous liquids that exist that inherit these same properties that we're looking at here. And then we go through here, and then so here's our viscosity versus our essentially we're measuring our shear rate, right? And then again, an excellent representation of exactly what we would expect to see with non-Newtonian liquids. So we would expect to see graphs like this and results like this, purely lining up with essentially like how overall expected behavior. And then again, more tests here. Viscosity versus time step. Again, proving out like there's not a huge like there's small correlation, right? I like it's not zero that's coming up on these, but it's and you can, especially with the high viscosity, you can see that there's like something like a little blip there, right? And then you like there is like blips within this, so. Like perhaps I'm not measuring time accurately with my measurements. Perhaps there's something that I am missing within this. Like there could be dimensions of it that I'm like not fully measuring, right? I don't want to discount. Like I hope like anyone. The worst thing I want anyone to do is like come onto this in the future and then like just like okay, he said that there's no correlation between like this non-Newtonian liquid and time steps, so I'm just gonna like discount that entirely. Like no, I'm saying that like there's not enough for me in my measurements compared to every other measurement that I do within this for it to like be a area for me to like research more, and it's not an area of research that particularly interests me. I know a lot of people are very interested in like the time correlation here, and it's just like I'm more interested in like the bigger picture. So that's my overall thoughts on it. And then so going through more, and then so the next test is like next two big tests are right like hysteresis and viscosity with varying perplexities. So then again like testing very specifically data as a non-Newtonian liquid. These are like very specific non-Newtonian liquid tests, and then they score non-Newtonian liquid. And then like here's like viscoelasticity, so your recovery versus PCA components. And then in here we're looking at like essentially like the data, the metrics that we're looking at here, and this is as expected, right? What this means is that like if you say that like you data is a structure, is a building, and then if I took like a wrecking ball to it, if it was a physical building, if it was a solid, taking a wrecking ball to the building would like blow out the entire wall, right? There would be like 100% damage to the wall, and I wouldn't be able to reconstruct the wall once the wrecking ball blows out the wall. What this shows is that, especially within the high viscosity data sets, that there's recoverability, and a lot of recoverability, like above 50% recoverability. So it's not a solid, right? It's more like a non-Newtonian liquid between a solid and a liquid state, where you could blow out the wall and it would crack, and it would probably put a hole in the wall, but the hole could heal itself, right? And it would, and the crack would heal itself, and you'd have some sort of healing effect, but not 100%, right? Like, it wouldn't fully recover from it. It would recover from it like 66% in the high viscosity test, essentially, right? It's kind of what you get from that. But so essentially, all of these tests combined show us and allow us to come up with the equation that we put for the top here for mathematical, like the mathematical equation that we come up with for data, proving out that essentially data itself is a fluid structure. And then so the next step within that then would be, okay, so data itself is a fluid structure. That doesn't prove that AI networks are a fluid structure. And then it could be disproven that if AI networks don't work via fluid structures, then data isn't a fluid structure, because, as put out and formulated in my proof at the top of this video, that there's a direct correlation between data and AI, because AI relies on data. So if AI is not a fluid structure, then data wouldn't be a fluid structure. So we go through this notebook of AI Navier-Stokes networks, and the bottom line here is, like, the most important part of this particular notebook is the last cell. The other cells are building up to it, but I'll show you everything that's in these experiments, right? So this notebook implements a deep learning model inspired by fluid dynamics, referred to as an AI Navier-Stokes network, or AI-NSN. The model is designed to incorporate neural ODEs, diffusion layers, and Hamiltonian mechanics to simulate fluid-like behavior and feature evolution during training. It's applied to the Fashion-MNIST dataset for classification tests. So using real-world dataset, you can, if you want to, on these tests as well, easily swap out these synthetic datasets for actual datasets. I've done it multiple times in other videos as well, which is why, like, I'm comfortable using synthetic here and then Fashion-MNIST here. And then so key differences of the AI-NSN model. So neural ODE block, continuous feature evolution, a neural ordinary differential equation, or ODE block, replaces traditional static layers, allowing feature maps to evolve dynamically over time, and uses the torch diff equation to library, so very specifically to solve differential equations within the network. I have a diffusion layer which simulates energy dissipation and turbulence. I have a divergence penalization for flow conservation and regularization. So the more that I treat it like a fluid neural network, like very specifically like a fluid, the more I'm able to tune the model, coincidentally. Hamiltonian neural network block introduces energy conservation principles into the model. So again, the more I'm tuning it via like a fluid, the more it functions better. Uses Hamiltonian mechanics to enforce structured learning by treating feature propagation as a physical system with conserved energy. Deep learning model with regularization, uses dropout layers to improve generalization, it includes batch normalization and ReLU activations to stabilize training, and employs the good old Atom optimizer with a learning rate of 0.001%. I don't know why, like, Atom is still like Atom is a fluid too, I guess. So implementations and so essentially going through this, like, the first steps that I do is proving out as can I model a neural network off of more fluid dynamic principles, right? So I take the Fashion-MNIST data set, and then that's exactly what I do. Is I take the GEMINI framework that I've established from there, and then I essentially directly correlate the GEMINI data framework into a model. So I apply PCA-based transformations to mimic viscosity to have it pass through the layers. Kind of like I give it kind of like I try to make PCA act like diffusion in this and flat out, right? And then see how that kind of works, and then just as like a base test, just like simple test, just to see how this goes. And then it works really well, right? Like the loss rates are good. I don't measure accuracy on this first test, and then I get 84% accuracy on the standard model and 80% accuracy on the Gemini model. And then so I'm like, okay, let me try to tweak that out more. Let me add more levers, right? So I add an adaptive viscosity lever, this Reynolds number inspired viscosity lever, feature flow propagation, memory effects. I start adding like shearing, Navier-Stokes smooth flow. Like I'm trying to like simulate more and more fluid dynamic flow in this instance, and then it has effect on the model. Like it doesn't change the model very much overall within this. I was expecting it to change it more, but it improves the Gemini outputs literally just by essentially treating it more like a flat out fluid dynamic model, right? Like all I do in this instance is I add more fluid dynamic inspired elements to the model, and it increases accuracy by 3% in this instance. And then so it's like, okay, cool. Let me like go deeper into that, and let me go like kind of ham into that, and then it drops to 16%. I'm like, okay, I did something wrong there, right? Let me go back and try to fix that overall, and then I get it back up to 82.75%. I'm like, okay, I'm back on the right track, but I'm still not beating that original 83%, right? And then so of the traditional neural network, and then I finally do it here, 84.80%. Again, I'll give you all of the. I want anyone that wants to dive into these experiments fully. Like maybe there's something that this guy missed in his experiments. Here's every single Colab notebook. Here's my GitHub repository. Feel free to dive into every single element of it, all my experiments, and tell me where I went wrong. And then so within this. I do essentially more like fluid tests within this, right? I add more fluid dynamics, so flow stability control. I add to suppress turbulence. I'm doing all elements that you would add to a fluid dynamic system, and then that's how I get it to the 84.9%. And then I'm like, can I get it even higher? 89.5%. So I beat out the traditional neural network by 10% in this instance, so by a significant margin, very significant margin overall, by just doing simple tweaks and like pulling levers with regards towards making this fluid network more fluid. And then, but this last representation isn't a full AI Navier-Stokes network, which is what I want to like prove out to you fully by the end of this video. So that's here, this last cell. It's still running and fully executing. I was hoping it'll be done, like fully training by now, but as you can see, I'm running that on CPU right now. You could run it on GPU and it would have been done a long time ago. But it's loading the data set, again, fashion MNIST in this instance. And then so this is where kind of the real magic happens. You can see that there's like, I put in like all of the elements, traditional elements. This is more fluid than computer. Like this is the origins of like liquid computing, and then so like you have neural ODE block, your diffusion layer, your divergence penalization, your Hamiltonian neural network block itself. Then you have you put all of that together, and then that gets you your full model with all of the connected layers. We calculate divergence loss before flattening. So we're putting it we do like that flattening in that whole PCA. So we have diffusion, and then on top of the diffusion, we have our PCA that acts like diffusion. So we've got a bunch of liquid states going on in here. Like we're shaking it up like a liquid a lot. And then we go through, and then we're just running our metrics. And then as you can see here, it's almost done, but like the loss rates are like very comparable to what I was getting with those models that was scoring between like 84 and 89%. I don't know where it's gonna come out. In that end, that would be my expectation here between 80, let's say 80 and 89. If you're extremely interested in how this clocks out, I'll leave, like you can check out this after it runs, and it'll be in this Colab notebook here. But so you have everything here at this point proving out what I've laid out here at the top of the video, the very top. So in conclusion, we redefine AI through the lens of fluid dynamics, proving that AI is governed by these same physical laws as flowing liquids and gases. There it is. If you like this type of content, please like and subscribe. Thank you very much.